Good morning, students. Today we are going to see the anomaly detection techniques for identifying abnormal process conditions. So, the outline of today's presentation is to understand the importance of anomaly detection in chemical process, differentiate between types of anomalies and their detection techniques. The third point, apply statistical and machine learning based anomaly detection methods. Fourth, interpret the anomaly detection results in chemical engineering application. This is what we are going to see in today's lecture. So what is anomaly detection? Anomalies or outliers are rare data points or events that deviate significantly from the majority of the observations. For example, in the last class also I told you, let's say doing the time series analysis, when we try to collect the data with respect to time, okay, either it may be a temperature or pressure of a reactor, okay, we will get some readings. So with respect to time. So during this process, what may happen, there may be a deviation of data, okay, because of the some disturbances that may occur, so that need to be rectified. So the importance in chemical engineering, so why we need to find the detection, anomaly detection, is the early detection of equipment failure, so that we could able to predict, we can able to identify is there any chances of equipment failure because of the deviation of data which has been obtained in the normal process conditions. So the pump cavitation, heat exchanger fouling, that may be prevented, okay, because of the early detection. Second point is prevention of hazardous condition. Example, temperature runway in reactors, quality assurance and regulatory compliance. These are the advantages of doing the anomaly detection. Prevent accidents like thermal runaway, which has been told hazardous condition. Saves money by reducing the downtime period. So if there is any failure happens, obviously that will leads to a downtime period. So as we know in industry, it will be operated 24/7 in 3 shift. Okay, obviously during the downtime period that will reduce the production. Okay, so if the production has been reduced, obviously the cost will be increased. Okay, so it helps in preventive maintenance. So these 3 points prevents accidents, that is a failure. Okay, so saves money by reducing the downtime period and helps in preventive maintenance. So these are the advantages of doing a anomaly detection. Okay, and coming to the different types of anomalies, the point anomalies, contextual anomalies and collective anomalies. What do you mean by point anomalies? Single abnormal readings, sudden spike in pressure. So let's say, as I told you, you have a reactor, you want to measure the temperature or pressure. Let's say I want to measure the temperature or pressure inside a reactor with respect to time. Or just take a distillation column and try to find the pressure with respect to time. So it's a single parameter determination. So if there is any deviation compared in a sudden changes in values, so is a that type of outliers is called point anomalies. Coming to the contextual anomalies, abnormal in a specific context. Example, high flow at low temperature. So is a contextual anomalies. So at high flow we have a, at low temperature there is a high flow. Okay, high flow at a low temperature. Collective anomalies. So because of deviation there may be some shift. For example, the gradual pH drift may be identified during the process. So this type of anomalies is called collective anomalies. So the sequence of values deviates. For example, fermentation. Okay, because of the process, okay, what happens? There is a change in pH drift. Okay, so this not because of the one varies values, it may be consequences. It's a sequence of values. These anomalies may be happen because of the sequence of values deviates. It's not only a single point. So point difference between the point anomalies and the collective anomalies. The point anomalies is the temperature or pressure that is deviating. So the collective anomalies, there is a shift in the pH that is maybe because of the different values, sequence of values. So that's why it's called collective anomalies. So we have separated the anomalies into three types. One is point anomalies, contextual anomalies, and collective anomalies. So what is anomaly? Anomaly is a rare data points or events that deviate significantly from the majority of the observations. That's why we are just trying to find out the deviation and make sure, as for the preventive maintenance, we are just make sure that deviation should not occur. Okay, hope you understood now. So what are the techniques how to determine the anomaly detection techniques? So there is a two method mainly has been classified. One is a statistical technique, another one is machine learning technique, are the combine of two techniques, that is called hybrid approaches, combine of statistical plus machine learning. Coming to the statistical techniques, it has been classified as z-score, standard deviation method, control chart, principal component analysis. So the reduction in number of variables. So when I say principal component analysis, immediately on your mind, what you supposed to understand, reflect is that, okay, the number of variables reduction. Chemical engineering example for this statistical technique: detecting abnormal pressure in a distillation column using control chart. So a pressure deviation or plus or minus 3 times of sigma, that is standard deviation, flag a potential issue due to column flooding or tray damage. So we should know the mean standard deviation. If there is a standard deviation is more than plus or minus 3 times, we need to show the system supposed to show a flag. So why this deviation occurs more than the 3 times or more less than the 3 times of the standard deviation. Okay, so hope you understood. So this is a control chart. And machine learning technique, unsupervised method against supervised method. Under unsupervised method, we have clustering. Example K means isolation forest, autoencoders, that is a deep learning. Supervised methods, if labeled data is available. So you know already, we have already discussed in unit 1 what is labeled data, what is unlabeled data, unclassified. Okay, the classification of different types of algorithms. Okay, I don't want to get into the again back to the supervised and unsupervised learning. So under which the machine learning techniques will help you to find the anomaly detection techniques. Okay, anomaly detection. Okay, by either by the supervised method or unsupervised method. Unsupervised method has been classified into three categories: clustering, isolation forest. Okay, not limited to only three. I just mentioned three here. Autoencoders. Supervised methods: classification algorithm, support vector machine, decision trees, time series based forecasting, plus residual thresholding. Chemical engineering example for supervised methods. Using unsupervised method they have given here. Using isolation forest to detect abnormal cooling water flow rate in a heat exchanger network, which may indicate fouling or malfunction. So let's say abnormal cooling water flow rate in a heat exchanger network. So the heat exchanger network, we have a cooling water flow rate which may indicate the fouling or valve malfunction. So the flow rate may vary because of the malfunction of the heat exchanger. Okay. So to detect the abnormal cooling water flow rate in a heat exchanger which may indicate fouling or valve malfunction. So if a flow rate is required larger, obviously there may be chances of the fouling takes place in the heat exchanger. So because of that, or near or something, so it get heated up. So because of that, the flow rate is increasing. Okay, so using isolation forest, the anomalies have been detected by using the machine learning techniques. And coming to the hybrid approach, that is a statistical and machine learning. Example is principal component analysis for future reduction and isolation forest for reduction. So anomaly detection by using a isolation forest for detection. For future reduction, we use the principal component analysis. Okay, the example here for detecting a hybrid approach: detecting temperature profile deviation in a batch polymerization using principal component analysis and autoencoder hybrid. Okay, so what are the evaluation metrics which are available? after you have find it out the anomaly detection by using a statistical or a, machine learning or hybrid method. Okay, precision, recall, F1 score. Okay, receiver operating characteristic area under the curve for binary classifiers, domain specific validation. Okay, for chemical process knowledge. Okay, so this one what it indicates is to know the process. Okay, domain specific validation is needed. Okay, by having a chemical process knowledge. So even in softwares, those who are dealing with the chemical engineering process, obviously they should have an understanding of the principles, again chemical engineering principles of that particular process. Either for example reactor, distillation, and so on and so forth. So the it's not only limited. Okay, it's not only limited only for I mean the chemical engineers also could able to, it's not only limited for engineers can only go for technical thing, they can also can adapt their knowledge into the software skills as well. Okay, so coming to the case study, so anomaly detection, so reactor temperature anomaly detection. So that is the one example which I am going to show to you, okay, as a case study. Okay, how the temperature, let's say you have a reactor and every seconds you are measuring the temperature of the reactor. Okay, if there is any deviation of normal values, how to find it out. Okay, let's see the scenario over here. The reactor temperature data over 30 days. Okay, so for every 10 second or every 1 minute, just measure for 30 days. Shows gradual deviation due to fouled heat exchanger. Okay, let's say you, as I told you, if you have a fouled heat exchanger, the water flow rate may be required high. Okay, or there may be changes in temperature. Okay, which you could not be able to see in a normal values readings. Okay, because it is a cumulative of after 30 days only it will be reflected there. So in order to find that type of anomalies, pre-processing and smoothing time series, the first part is the pre-processing and smoothing time series, and apply exponentially weighted moving average control chart, and third one train isolation forest for residual detection, compared flagged anomalies with known maintenance logs. So after 30 days and the first day, how it varies. Okay, so the flagged anomalies is a under control limit or a lower control limit, upper control limit or lower control limit. Okay, so I will show an example with MATLAB coding. Okay, how this need to be carried out for the anomaly detection. Okay, that I will show in today's lecture itself. Okay, so the outcome is yearly anomaly detection before threshold breach prevented thermal runaway. So yearly anomaly detection, what is the advantage? This is like a preventive maintenance. Okay, anomaly detection before threshold breach prevented thermal runaway. In a chemical reactor, temperature control is critical for safety and product quality. There is no doubt about it. Okay, because increase in temperature, it also not favors sometimes, for example, absorption or what you called reactor, the process need to be carried out. Temperature control is must. For example, at constant temperature, the reactor need to be allowed to react. Otherwise, what will happen? Okay, so the temperature control is critical for safety as well as the product quality. That's what they mean. A fouled heat exchanger, okay, one that is clogged with the residue, can reduce heat transfer efficiency. This leads to a gradual rise in reactor temperature. So if the heat exchanger is working properly, there is no problem. Otherwise, what will happen? A fouled heat exchanger can reduce the heat transfer efficiency. This leads to a gradual rise in reactor temperature, a slow but dangerous deviation. Okay, so you could not be able to predict actually very small changes, but that need to be noted down and that need to be visualized so that this will avoid the unwanted process, unwanted occurrence that may occur. If not detected early, this can lead to thermal runaway, a uncontrolled increase in the temperature. So, what are the steps? Pre-processing and smoothing time series. Raw temperature data may contain noise. So, we need to make sure there won't be any fluctuation. So, in the time series analysis, in the last class when we talk about, we also talk about the sensors which will help you to determine the values. So, if there may be chances of fluctuations in the values that need to be taken care of. Okay, raw temperature data may contain noise. Apply smoothing techniques like moving average. or exponential weighted moving average. EWMEA means exponential weighted moving average to reveal the underlying trends, handle missing values or outliers during this step. So what is the purpose of this? Doing a pre-processing and to smoothing time series. Raw data may contain noise, so apply smoothing techniques, try to reduce the noise values and handle missing values or outliers during this step. Apply engineered weighted moving average control chart. Okay, track small shift in process mean over time. More sensible than shivered chart for detecting the slow trend. So it's more sensitive. Okay, so when compared to the shivered chart, there is a very small variation. This is more sensitive. Engineered and exponentially weighted moving average. Plot control limit, upper control limit and lower control limit around expected values. If the smoothen temperature drifts outside control limit, is flagged as an anomaly. So if the temperature is outside the control limit, obviously this will help you to find it out. This flagged as an anomaly, that is a deviation from the normal. So we will fix the upper control limit and lower control limit. Train isolation forest for residual detection. So that is third step is train isolation forest. So how to do it? After removing the expected train using smoothing, the residuals are passed to a machine learning model. Isolation forest is an unsupervised algorithm that detects the anomalies by isolating the data points. It is good for multivariate data, for example, combination of data, combining temperature with pressure or flow rate. So, multivariate data, it is helpful. Okay, the isolation forest unsupervised algorithm detects unusual pattern that our control chart might miss, especially the complex interaction. So, why we need to go for combined techniques, the anomaly detection, either statistical or residual, supervised machine learning, because that will help you to find it out more fine tuning, so that it will help you even a small detection in variation that can be get caught. And compare flagged anomalies with maintenance logs. So the model flagged anomalies are cross-checked with the historical maintenance data. So if there is any deviation, okay, above the upper control level, or what you call it UCL, and previously we have just told lower control level. Okay, so in that values, if the values is considered away from the value, the record data, historical data, that will be flagged as an anomaly. Okay, so the models flagged the anomalies are cross-checked with the historical maintenance data. For instance, if an anomaly was detected on day 23 and log shows exchanger cleaning on day 24, the detection was accurate. This step validates the detection method and can be used to improve the future alert system. Okay, so what is the chemical engineering perspective? How you see this thing? Okay, this is a classic example of predictive maintenance. Fouling is a common issue in heat exchanger. Everyone knows, used in distillation, okay, reactors or condensers. Traditional monitoring would miss slow trends, but combining statistics and machine learning gives better visibility. So underline the word by combining the statistics and machine learning. The machine learning is a supervised method or unsupervised method. Okay, so that's why the combined method is always more precise to identify the anomalies. And the summary so far what has been covered is the anomaly detection is essential for safe, efficient chemical plant operation. Okay, it is mainly useful for safe and efficient process optimization. Okay, efficient chemical process operation. Choose methods based on data type and availability of labels. Combine domain knowledge with analytical models for best results. So anomaly detection techniques. So we are going to see one assignment on anomaly detection on distillation column data. Okay, and I am going to explain the codes of the MATLAB. So how this can be carried out. Let's say the distillation column. Okay, use control chart isolation forest to detect the anomalies in flow rate and pressure data from a distillation column. Let's say you have a distillation column. If there is any changes in pressure data during the process time period, let's say for a, because usually in industry you have a 24 by 7 operation. Let's say the distillation is operated for 30 continuously for 30 days or something, or Shutdown. Okay, so during the process, how the pressure has been maintained inside the distribution column. That's what we are going to see. We are going to flag it out. Okay, any anomaly detection has been identified during this process. How to do about it? Okay, so anomaly detection on distillation column data. The focus is flow rate and pressure data. So, exponentially weighted moving average control chart and isolation forest has been used for the conceptual implementation in MATLAB. Coming to the step 1 doing this process. So, the range 42 for reproducibility. Let's say n is equal to 200. The flow is 100 plus 5. The 100 is mean, standard deviation is 5. So, the random, okay, n comma 1 generates normal random numbers. Flow and pressure stimulate real-world measurements from a distillation column. Okay, range 42 ensures that each run gives the same random numbers. So, the step 1 is stimulate the data for flow rate and pressure. The second step is inject artificial anomalies. Let's say the flow spike, stimulate a leak or feed surge. So, plus 20, okay, the flow for pressure is 0.3 dip, pressure dip. Okay, so simulating the valve or sensor failure. So, introduce abnormal condition to test anomaly detection logic. The second one is inject artificial anomalies. The deviation inject artificially, just do the thing. So EWMA, that is a moving average, that is a exponential weighted moving average. In that lambda is equal to 0.3. EWMA, that is a filter. By using the filter we adjust lambda minus 1 pressure. Okay, engineer weighted moving average, we are just giving them a upper control limit and lower control limit, okay, for the control chart. So by using the filter, calculate the exponential weighted moving average using recursive filtering. So the upper control limit and lower control limit define control boundaries. So within this range is not detected as a anomaly. If it is above or below this range, obviously it will be counted as a anomaly, that is a deviation, and marked as a flag. If the smooth spring crosses this, it is considered anomalous. Plots exponential weighted moving average control chart. How to plot? By using a MATLAB code. Plot pressure versus, okay, so pressure versus what you call it, x label time pressure, y label is pressure, x label is time. The legend has been used the actual pressure and the engineer exponential weighted moving average. The blue line is raw pressure. Okay, so we are giving a color line. Okay, hyphen R means red color, hyphen G means green color. Okay, so blue line is a raw pressure. Okay, and red line is a smoothed engineer weighted moving average. Green and red dashed line control limit. Hope you know how to do the MATLAB code. This is a normal, very simple thing. Plot. They were asking the chat to plot. Okay, so that is the fourth step of the MATLAB code. And coming to the step 5, isolation forest for anomaly detection. So we are going for a unsupervised learning. So MATLAB does not have a built-in isolation forest, but we stimulate it using a code called fin sensible and anomaly scores. Let's say x is equal to flow pressure, MDL, the fit sensible, x1 n comma 1 method back, number learning cycle 100. Okay, and then we also use the who predict MDL. Okay, so use back the ensemble trees to stimulate the isolation forest behavior. The idea is normal points are deep in trees, anomalies are isolated yearly. The score used as a proxy for anomaly likelihood. So the above are the codes. The X, MDL, anomaly score, the 3 points are the code in the MATLAB. So why we are using, how we are using actually, so that has been given over here reason. Coming to the point number 6, again the figure scatter value 1:9 flow 30 anomaly score field color bar. Title is anomaly detection using isolation process. Stimulated one, x label time, y label is flow rate. Okay, or else you can also give a pressure. Okay, a color scatter plot where deeper colors is equal to higher anomaly score. Else visualize when flow rate deviates unusually from the trend. So what are the codes which can be used actually during this processing by using a MATLAB, that I would like to mention here. So anomaly detection, we have just now used the fin sensible or OOP predict. Visualization, plot, scatter, color bar, control chart limit. We can have a syntax of MATLAB, mean, standard deviation, y line, a exponential weighted moving average, filter, data stimulation, okay, synthetic injection or random number. Okay, so this is how the MATLAB code need to be written. So I just would like to show an example how to do the anomaly detection when during the process. For example, the pressure deviation which has been happened in the distillation. Okay, so what is the advantage of this anomaly detection technique? Control chart detects the slow process shift. Ensemble tree-based anomaly detection finds complex pattern across multiple variables. Example, when high flow and low pressure indicate a leak. So, ensemble tree-based anomaly detection find complex pattern across the multiple variables when high flow and pressure indicate a leak. This enables real-time fault detection in units like distillation column, reactors, and heat exchangers. Or actually identifying the anomaly detection will help you to save process as well as the optimization. I mean, we could be able to do the process without any disturbances. Okay, that means we can identify the faultings which may occur by knowing the variations. So, if we see the technique, anomaly detection technique, these are the techniques, that is statistical techniques or machine learning techniques or hybrid techniques. So, how it works? So, they are with an example I have given over here. Control chart like exponential weighted moving average detect small changes in process values like temperature or pressure over time. So example in process finds slow heat exchanger fouling. So the control chart has been can be used, okay, for this type of anomaly detection. So Z-score statistical method check if the wall is far from the average, detect sudden drop in the flow rate. Okay, so for example, the cooling water is increased flow rate has been found. So, or there is a drop in flow rate. Okay, then we can go for a statistical method or Z score. Okay, so machine learning like isolated forest, okay, learns from the normal data and flags anything different. So, isolated forest we need to have a historical data. If there is any deviation, then that can be easily can be find out. Find unknown issues in complex systems. Okay, principal component analysis reduces many variables to key patterns and find the changes. As I told you, principal component analysis, number of variables is getting reduced. Reduce, underline the word, reduces many variables to key patterns and find changes. Monitors distillation column efficiency. Auto encoders or deep learning learns compact data representation and flags anomalies. Okay, deep learning learn compact data representation and flags anomalies and identify the anomalies plus or minus 3 standard deviation. Example, okay, from reconstruction error detects change sensor patterns. Okay, so this is how there are different techniques which are available to for the anomaly detection and how it works. What are the examples which have been given here for your ready reference. Okay, so I just would like to wind up this section. Okay, so what we have seen today, what is anomaly detection, what is the advantage, what are the different categories of anomaly detection. Okay, so how to do the detection techniques. Okay, that's what we have seen. So the main learning of today's class is nothing but understand the importance of anomaly detection in chemical process, differentiate between types of anomalies, that is types of anomalies has been noted, point anomalies, contextual anomalies and collective anomalies, and apply statistical and machine learning techniques to detect the anomalies and interpret the anomaly detection results in chemical engineering application with an assignment of and MATLAB code I have explained to you. Hope you understood today's section. If you have any doubt, please feel free to ask me during the face-to-face section. With this note, I just try to wind up the today's section. Thank you for your time.